Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where your thoughts can drift, and science becomes a gentle companion to the night. Tonight, we're venturing into one of the most mysterious stories ever told by the universe itself. It's a story about something we cannot see, cannot touch, yet it's reshaping everything, from the smallest atom to the farthest galaxy. A silent presence known as dark energy, the force that doesn't just move things but moves reality. Before we begin, I'd love to invite you to get comfortable. Maybe dim the lights, let the glow of your screen soften, and settle into that quiet space between curiosity and calm. If you enjoy these slow journeys through the night sky, you're always welcome to like this video or subscribe. Only if it feels right, of course. And when you're ready, let me know in the comments where in the world you're listening from and what time it is in your night. It's always a wonder to imagine all of us scattered across time zones and continents, united by this shared curiosity about the universe and its strange, invisible rhythms. Now, take a slow breath. Feel your chest rise and fall like the tide of a distant ocean. In this stillness, we'll begin to explore the most subtle of cosmic mysteries, the quiet acceleration of everything, everywhere. You don't have to stay awake for all of it. Just let your mind drift and I'll keep the story going, gently unfolding the tale of how the universe learned to run away from itself. It started not with a bang, but with a flicker. Tiny points of light in the night sky, each one a distant star's farewell. A supernova, caught in the act of fading. In the 1990s, two teams of astronomers set out to measure how fast the universe was expanding. They expected to find that over time the cosmic expansion was slowing down. After all, gravity pulls everything together. It should be gradually tightening its invisible grip, turning the universe's outward rush into a long, slow glide. But when they measured those faint explosions at the cosmic mile markers scattered across billions of light years, something unexpected appeared. The light wasn't just dim because it was far away, it was dimmer than it should have been. That meant those supernovae were farther than anyone had predicted. The galaxies hosting them weren't slowing down, they were speeding up. The universe was not coasting gently into old age. It was accelerating, as if pushed by a force no one had ever seen. Imagine that for a moment. Galaxies, whole cities of stars drifting apart faster and faster, not because they are moving through space, but because the space between them is growing. The very fabric of reality itself, expanding like dough rising in an oven, stretching everything within it. And the more it stretched, the faster it expanded, like a breath that never ends. Astronomers were stunned. The numbers made no sense. Every law of gravity said this couldn't happen. They double-checked the data, recalibrated the telescopes, compared the brightness of dozens of supernovae across the universe. But the result held true. Something unseen was overpowering gravity on a cosmic scale. It was as though a silent wind was blowing through the universe, urging galaxies apart. This discovery changed everything. For decades, cosmologists had believed that the universe's expansion, born from the Big Bang, would gradually slow down. Some imagined it might stop one day and collapse, a big crunch, where everything would fall back inward. But this new finding told another story. The expansion wasn't fading, it was accelerating. The universe was not just expanding, it was running away from itself. At first, scientists didn't know what to call this invisible force. Some called it vacuum energy, others the cosmological constant. Eventually one name stuck: dark energy. Dark, not because it was sinister, but because it was unknown, unseen, unfelt, untouchable. It doesn't shine, it doesn't absorb light, and yet it fills all of space. The magnitude of it is staggering. Everything you can see, stars, planets, galaxies, dust, gas, even dark matter, makes up only a small slice of the cosmic pie. Roughly 5% of the total, the rest is invisible. about 27% is dark matter, the hidden scaffolding holding galaxies together, and about 68% is dark energy, an unseen pressure that drives the cosmos apart. In other words, most of the universe is made of something we don't understand. But here's the strange part. This mysterious energy doesn't act like anything we know. Ordinary matter clumps together. Gravity pulls it inward. Dark energy seems to do the opposite. It spreads evenly, everywhere, like a constant breath pushing outward on the edges of existence. It doesn't weaken as space expands. In fact, the more space there is, the more dark energy there seems to be. Imagine stretching a sheet of rubber, and instead of thinning, it creates more rubber as it stretches. That's how baffling this is. Space itself might be creating more of itself. At the heart of this idea lies something Einstein wrote long ago. In his equations for general relativity, he added a small term, a kind of cosmic correction, to keep the universe stable. He called it the cosmological constant. Later, when Hubble discovered that the universe was expanding, Einstein regretted it. He thought it was his greatest mistake. But now, a century later, that mistake might be the key to understanding why the universe accelerates at all. It seems the universe had been whispering its secret for 100 years. That empty space is not empty at all. If this is true, then the vacuum itself, what we think of as nothing, has energy. A quiet, persistent pressure woven into the fabric of space-time. Even when you remove every atom, every particle, the void still hums faintly with potential. In the quantum view, tiny fluctuations ripple through the vacuum constantly. Particles appearing and vanishing in pairs, leaving behind a whisper of energy. Add up those whispers across the infinite cosmos, and you might get something that looks like dark energy. It's an unsettling thought, isn't it? That nothingness itself could be alive with motion. That the silence between galaxies could be the most powerful force in existence. Yet, in its calm persistence, dark energy has shaped everything we see. It determines not just how galaxies move, but how time flows, how matter evolves, and how the story of the universe will end. So tonight, as you lie there and listen, remember, the stars above you are drifting apart even now, carried gently on the current of an unseen sea. The universe breathes, expanding slowly, silently, endlessly. And though it feels distant and vast, that same expansion is happening here too, between you and every atom of the world around you. The cosmos stretches softly with every passing second, and somewhere, in that quiet motion, the story of dark energy has only just begun. Before that revelation in the late 1990s, the universe seemed almost predictable. Cosmologists believed they were tracing a grand but orderly story that began with a single blinding event, the Big Bang. From that initial burst of creation, everything had expanded outward like ripples on a pond. Galaxies were born, stars ignited, planets formed, and time itself unfurled along a path that, while immense, felt understandable. Gravity, the steady hand of the cosmos, was expected to slow that outward rush, tugging gently on galaxies the way a mother might draw her child back toward home. It was such a simple picture. The Big Bang sends everything flying outward, and gravity, universal and unrelenting, tries to pull it all back in. Depending on which side won, the universe would face one of two fates. Either expansion would continue forever, gradually easing into stillness, or it would eventually stop, reverse, and collapse into a fiery end. A big crunch mirroring the Big Bang in reverse. It was elegant, self-contained, almost poetic. To understand how revolutionary the discovery of acceleration was, we need to step back into Einstein's time, to the early 1900s, when he was writing the equations that would become the general theory of relativity. Those equations described how matter tells space how to curve, and how curved space tells matter how to move. Gravity, in Einstein's view, wasn't a force in the traditional sense. It was geometry. the way the fabric of space and time bends around mass and energy. But when Einstein applied his equations to the entire universe, something strange happened. The math didn't allow for a static, unchanging cosmos. It either expanded or contracted. At that time, most scientists believed the universe was eternal and unchanging. To make the math fit the philosophy, Einstein added a small term to his equations, a gentle outward pressure that balanced gravity perfectly. He called it the cosmological constant, a steady energy built into the fabric of space itself. In effect, he created a cosmic seesaw. Gravity pulled inward, the constant pushed outward, and the result was a calm, timeless universe. Then, in 1929, Edwin Hubble shattered that illusion. Using the Great Telescope at Mount Wilson, he discovered that galaxies are moving away from us, and the farther they are, the faster they recede. The universe wasn't static, it was expanding. Suddenly, Einstein's balancing term was unnecessary. He abandoned it, calling it his greatest blunder. The cosmos didn't need a hidden push. It was already on the move. For most of the 20th century, that view held strong. The universe expanded, but gravity was expected to slow it down, just as a ball tossed into the air slows as it climbs. Even when we didn't know the exact numbers, the idea felt intuitive. A grand explosion followed by a long, graceful deceleration. The only question was whether the universe had enough matter to eventually pull itself back together, or whether it would drift endlessly into the dark. That's why the discovery of acceleration hit with such quiet force. It overturned nearly a century of assumptions, not just about physics, but about the story we thought we were living in. The cosmos wasn't slowing down, it was speeding up. The great ball of the universe wasn't coasting upward through gravity's air. It was being pushed higher by some invisible hand. And if that was true, it meant that empty space, what we call the vacuum, wasn't truly empty at all. In the modern picture, space itself is alive with a faint, persistent energy. When physicists describe this, they use something called the cosmological constant, the same idea Einstein once introduced and then discarded. But this time, it isn't a mathematical trick, it's real. Instead of seeing it as a static counterweight to gravity, scientists now think of it as an intrinsic property of space, a kind of pressure that exists everywhere, always the same, no matter how much space there is. The more the universe expands, the more of this energy there seems to be, because new space is always being created, and each tiny region of space contributes its own portion of energy to the total. The result is an expansion that feeds itself. It's as if the universe is earning interest on its own emptiness. Every second it grows a little faster than the second before. You can imagine this as a fabric stretching under tension. Gravity tries to weave the threads together, forming galaxies and stars, while this mysterious energy tugs in the opposite direction, loosening the weave. Over vast distances, the tug of dark energy wins, not through force, but through persistence. It's not a sudden shove, it's more like a steady breath, a constant sigh that never ends. What's most curious is that this energy acts uniformly. It doesn't cluster or clump the way matter does. If you could somehow zoom out to see the entire universe as one vast web, you'd find galaxies linked in strands and filaments, the cosmic web, and between those luminous threads lies an ocean of space, expanding in every direction. Dark energy is that ocean, perfectly smooth, perfectly indifferent, carrying everything within it. Even now, scientists can only describe it, not define it. We measure its effect, galaxies receding faster, light stretching into longer and redder waves, but we still don't know what it actually is. Some think it's the energy of the vacuum itself. Others suspect it might be a field, a kind of cosmic background that evolves over time, stronger in some eras, weaker in others. This idea has a name, quintessence, the fifth essence beyond Earth, water, air and fire, a poetic nod to the ancients who once believed the heavens were made of something pure and eternal. If dark energy is truly a field, it might change. It might one day fade away or strengthen, rewriting the future of everything. In one direction lies a universe that expands forever, cooling into darkness. In another, a universe that tears itself apart, even down to the atoms that make us. And in between, perhaps a balance so delicate that only a universe like ours, capable of life, capable of wonder, could ever exist. But for now, we live in the brief moment when galaxies still share light, when the stars are still bright enough to be seen, when the echo of that first explosion still hums softly through the cosmic background, like a lullaby that never quite fades. The discovery of dark energy didn't just tell us that the universe is expanding faster, it reminded us how fragile our understanding can be, that even the emptiness we take for granted is alive with mystery. So when you look up at the night sky and the stars seem timeless, remember, the universe is still changing beneath that calm. Every beam of starlight you see is stretched a little more than it should have, as if the night itself were exhaling. We once thought we knew how the story would end, that gravity would have the final word. But perhaps in the silence between those stars, something else has already begun writing a new chapter of the cosmos. If you could hold the entire universe in your hands and sort it into its ingredients, the result would be both humbling and a little absurd. All the stars you've ever seen, every planet, every cloud of gas, every atom of gold and dust and water, all of that together would make up only a tiny fraction of the cosmos, barely 5%. The rest, the overwhelming majority, is hidden. Roughly 27% is something called dark matter, a mysterious scaffolding of invisible mass that holds galaxies together. And then there is the largest slice of all, about 68%, the part we call dark energy. It's not only the biggest ingredient in existence, it's also the one we understand the least. When astronomers first measured how galaxies move, they discovered something astonishing. The visible matter, the stars and gas we can see, wasn't enough to explain how galaxies spin. They should have torn themselves apart long ago. Something unseen must be providing the extra gravity to hold them together. That became dark matter. But the mystery of dark energy was even stranger, because it wasn't holding things together at all. It was doing the opposite. It was pushing everything apart. The discovery began with light. When light travels across the universe, it stretches as space expands. The farther it travels, the redder it becomes, shifting toward longer wavelengths. This redshift is like a cosmic fingerprint, showing how much the universe has expanded since that light left its source. By measuring how red the light from distant galaxies had become, astronomers could tell how fast those galaxies were receding. At first, they expected the expansion to slow over time, like a stone thrown into the sky gradually losing speed. But when they compared ancient light from distant supernovae to the glow of younger ones closer by, they realized the opposite was happening. The expansion was accelerating. It was as if the universe had pressed its foot on a pedal, hidden beneath the floor of reality, and no one knew what powered it. In the decades since, scientists have built a remarkable toolkit to study this invisible force. One of them is the cosmic microwave background, the faint afterglow of the Big Bang itself. When missions like Planck and WMAP mapped that glow, they found tiny fluctuations, patterns of temperature differences scattered across the sky. Those ripples, frozen since the dawn of time, are a kind of fossil record of the early universe. They tell us how much matter, radiation, and dark energy it contains, and they all agree the cosmos we inhabit is dominated by this unseen energy that accelerates its growth. Another line of evidence comes from something called baryon acoustic oscillations, delicate ripples in the distribution of galaxies that trace the sound waves of the infant universe. Imagine the young cosmos as a vast ocean of plasma, where waves of pressure travelled through the hot gas. As it cooled, those waves froze into the pattern we see today. galaxies separated by preferred distances. By measuring those distances precisely, astronomers can track how expansion has changed over billions of years. And once again, the story is the same. The expansion is speeding up. Even gravitational lensing, the way light bends as it passes through massive objects, reveals the same truth. When light from distant galaxies travels past clusters of matter, it warps and stretches. By measuring that distortion, astronomers can map the invisible mass of the universe. What they find is consistent everywhere. There's not enough normal matter or even dark matter to account for the way galaxies move apart. Some smooth, unseen energy must be acting across the entire cosmos, pulling it open like a tide that never recedes. At this point, scientists had more than one mystery. They had a balance sheet that didn't add up. The equations of cosmology, based on Einstein's general relativity, describe how the contents of the universe influence its expansion. On one side sits gravity, the pull of matter. On the other, whatever drives acceleration must have the opposite effect, a kind of negative pressure that pushes instead of pulls. The ratio between that pressure and its energy density is what cosmologists call the equation of state. It's usually represented by the letter W, but we can describe it more softly. It's the relationship between how much the energy weighs and how strongly it pushes outward. If this energy were a cosmological constant, as Einstein proposed, its value of W would be exactly -1, a perfect balance between energy and expansion. But if W drifts away from that number, the universe's fate could change dramatically. For now, every observation we have points to something very close to that constant value. A quiet, steady pressure woven into the vacuum of space. The strange part is that this energy seems to remain the same everywhere, even as the universe grows. As new space appears, more dark energy seems to appear with it, like a self-replenishing field. It doesn't dilute the way matter does when it spreads out. It simply keeps pushing softly, persistently. Try to imagine that for a moment. You have a balloon and you keep inflating it. The air inside thins out, becomes less dense, but the rubber itself somehow creates more air as it expands, keeping the pressure steady. That's what dark energy does to space. It makes more of itself simply by existing. It's a feedback loop written into the very geometry of the cosmos. Yet this picture raises deep questions. If dark energy is the energy of empty space, then how can the vacuum know how much energy to have? Quantum physics tells us that every cubic centimetre of empty space should be seething with tiny fluctuations, particles flickering in and out of existence. If we calculate the energy of those fluctuations, we get a number so enormous that the universe would have blown apart instantly. But in reality, the energy we observe is incredibly small, about 100 trillion times smaller than the theory predicts. That mismatch is one of the greatest puzzles in all of science. It's as if the universe finally tuned itself to balance on a razor's edge between collapse and runaway expansion. Maybe there's a hidden symmetry we don't yet see, something that cancels out most of the vacuum, energy, and leaves only a faint residue. Maybe dark energy isn't constant after all, but slowly changing with time, its influence waxing and waning like a cosmic tide. Or maybe, most unsettling of all, we're only seeing one layer of a deeper reality. A kind of multiverse foam where countless universes bubble into existence, each with its own version of physics, and ours just happens to have a vacuum that allows life to exist. These are not ideas of science fiction. They are serious attempts to reconcile observation with theory, whispered into the halls of cosmology by researchers who spend their lives measuring light that left its galaxies before Earth even existed. They stare at faint smudges of starlight, billions of years old, and try to read the universe's diary from its fading ink. And perhaps that's what makes this story so hauntingly beautiful. The more we discover, the more the universe seems to fade into mystery. We have learned to weigh galaxies, to listen to the echo of the Big Bang, to trace the bending of light across cosmic time, and yet what we understand accounts for barely a sliver of what exists. 95% of reality hides behind a curtain we can only describe in whispers. When you look at the stars tonight, know that they are outnumbered by the unseen. The galaxies themselves drift on a dark ocean whose surface we can never touch. And within that ocean, the faintest pressure of the vacuum is rewriting the destiny of everything. It is gentle, patient, and vast beyond imagination, the silent hand that sculpts eternity. If you could freeze time and look at the universe from far enough away, you wouldn't see stars racing across a dark void. You'd see something stranger, galaxies suspended in an invisible fabric, a cosmic web that stretches quietly, gently, in all directions. It's not the galaxies themselves that are moving through space. It's space that's moving between them, expanding like the slow breath of a sleeping giant. And the more space there is, the faster that breath becomes. This is what scientists call the accelerated expansion of the universe. But that phrase, while accurate, hardly captures its poetry. It's not a speed you can measure with a stopwatch. It's more like a rhythm, the quiet pulse of reality itself. You can think of the universe as a vast loaf of bread rising in an oven. The raisins inside it, the galaxies, are carried apart as the dough expands. None of the raisins are flying through the dough on their own. They stay still relative to the dough itself. It's the dough, the space, that grows between them. From any single raisin's point of view, all the others seem to be moving away, and the farther they are, the faster they appear to go. That's exactly what astronomers observe when they measure light from distant galaxies. The light stretches, its colour sliding toward red, a sign that space itself has stretched during its journey. It's as if every beam of starlight has been gently pulled like taffy across billions of years. This stretching doesn't happen at the same rate everywhere. On the small scale, within galaxies or even clusters of galaxies, gravity still reigns. The Milky Way isn't being torn apart. The pull of its stars and dark matter easily overcomes the cosmic expansion. The solar system, too, is safe within the sun's gravitational embrace. Even the space between you and the nearest star barely changes at all. But beyond the scale of galaxy clusters, the expansion wins. It's a slow, relentless push, one that only becomes visible when you look across hundreds of millions of light years. Astronomers describe this push through something called the Hubble constant, not a mathematical constant in the unchanging sense, but a rate that tells us how fast the universe expands at any given moment. For every million parsecs, a cosmic distance unit roughly equal to 3 million light years, galaxies move away from one another by about 70 kilometers each second. But even that number isn't fixed. It has changed over time and still sparks gentle debates between different telescopes, each measuring slightly different values. What matters most is not the precise number, but the trend it reveals. The expansion is speeding up, not slowing down. Every moment of cosmic history, the distance between faraway galaxies grows larger than the moment before. This acceleration carries a strange implication. As space expands faster and faster, distant galaxies slip beyond what's called the cosmic horizon, the maximum distance from which light can ever reach us. Beyond that horizon, those galaxies become permanently invisible. Their light will never arrive, no matter how long we wait. Every second, more galaxies disappear over that edge, not by fading, but by being carried away on the current of expansion faster than light can bridge the gap. It's not that they're breaking the speed of light, it's that space itself is stretching faster than light can travel through it. The horizon is like a tide line, forever receding, taking more of the universe with it. One day, billions of years from now, the night sky may hold only the faint glow of our own galaxy, adrift in infinite silence. If that sounds lonely, remember that this expansion isn't violent. It's delicate, almost tender. It happens everywhere at once, smoothly and silently. Space doesn't crack or tear. It simply grows. Every atom, every photon, every patch of the vacuum is part of the same gentle drift. The universe doesn't explode outward like a firework. It exhales, calmly, eternally. The galaxies we see today are like dust motes caught in sunlight, drifting apart on the slow breath of creation. What powers this expansion still defies easy description. In Einstein's equations, the cosmological constant represents a uniform energy density filling all of space. It's a number so small that it barely influences local motion, yet when summed across the whole universe, it dominates. If you imagine each cubic meter of space holding a whisper of this energy, the effect is negligible nearby, but multiply that whisper by the vastness of the cosmos, and it becomes the loudest voice in existence. It's the difference between a single raindrop and an endless rain. One drop is nothing. The whole storm shapes the world. The acceleration also alters time itself in subtle ways. In regions where dark energy dominates, time stretches differently than it does where gravity holds sway. It's not something we can feel. No clock on Earth runs slower because of it. But across cosmic distances it matters. The future of the universe depends on this balance. As expansion continues, the density of matter thins, but the energy of the vacuum stays constant. Eventually, dark energy will outweigh everything else entirely. Then the cosmic acceleration will no longer be subtle. It will define the rhythm of time, the structure of space, and perhaps even the possibility of memory. Think of the early universe as a symphony of competing melodies. First came radiation, a blinding storm of light dominating the score. Then matter took over, shaping galaxies and stars, giving structure to what we see. Now, dark energy leads. Its note is softer, almost inaudible, but it sets the tempo for everything else. We are living in the movement of the symphony where the music slows, grows spacious and begins to fade. Yet even as it fades, it opens new harmonies, room for wonder, for stillness, for the awareness that we exist in a living, breathing universe. What's remarkable is that we can measure this cosmic breath at all. From a small planet orbiting an ordinary star, we've learned to read the sky's slow heartbeat. We watch galaxies as they drift through time, their light stretched across billions of years, and from that light we infer the invisible. The instruments we use, the telescopes, the detectors, the satellites, are like ears pressed against the fabric of the universe, listening for its quiet expansion. And what we hear is a whisper that began long before there were stars to listen. Every photon reaching your eyes tonight has travelled through this stretching space. Its wavelength lengthened, its colour softened. You're seeing not just the light of ancient stars, but the history of the universe written into that light. Each beam is a message. I left long ago, and the space between us grew while I travelled. Even the starlight entering your window carries evidence of the cosmos's silent acceleration. There's something almost comforting in that thought. The same quiet expansion that carries galaxies away also carries you through time. It doesn't rush. It doesn't shout. It's the calm heartbeat of creation itself, beating beneath everything we know. So as you listen now, perhaps with your eyes closed, your breath slowing to match the rhythm of the story, imagine the universe not as a place moving apart, but as a single living thing, expanding softly, endlessly, in all directions. The galaxies, the stars, even you, are part of that gentle motion, the slow unfurling of reality's endless fabric. And in that motion, you're exactly where you belong. It's difficult to imagine, but the quiet emptiness between stars may be the most active place in the universe. When you look into a patch of darkness in the night sky, it seems calm, silent, perfectly still. Yet according to quantum physics, that darkness is not truly empty. It trembles with invisible motion. Tiny flickers of energy ripple through it, appearing and vanishing too quickly for even light to notice. This is the energy of the vacuum, the faint hum of nothingness itself, and it might be the key to understanding why the universe continues to accelerate. To grasp this idea gently, imagine the universe as a vast ocean that never rests. Even when no wind stirs its surface, the water still ripples from countless unseen currents below. In the same way, even the most perfect vacuum, a place without atoms, dust, or radiation, is alive with hidden fluctuations. The quantum fields that fill space never fall completely silent. They vibrate softly, constantly creating and destroying pairs of particles in the blink of an eye. You can think of them as momentary sparks in the fabric of existence, tiny blips of something out of nothing. Each of these flickers adds a whisper of energy to the vacuum, so faint that individually it's nothing, but together, across the immensity of the universe, they create an almost immeasurable pressure. It's this quiet pressure that physicists believe might be driving the cosmic expansion, the invisible hand that pushes galaxies apart. In simple terms, the vacuum itself has weight, or more precisely, it has energy. And because energy and gravity are connected, that energy can make space expand. Einstein's famous insight was that mass and energy are interchangeable, two forms of the same thing. He expressed this as the relationship between energy, mass, and the speed of light. The equation is short but profound. Energy equals mass multiplied by the square of the speed of a light. You don't need the symbols to understand it. All it says is that even a tiny amount of matter contains a vast amount of energy, because the speed of light squared is an enormous number. What we call empty space, when you look closely enough, might contain more energy than all the stars combined. But there's a problem. When physicists try to calculate how much energy the vacuum should have, based on quantum theory, they arrive at a number so large it borders on absurd. If the quantum vacuum really carried that much energy, the universe would have torn itself apart the instant it began. Yet observations show that dark energy is gentle, subtle, almost delicate, enough to accelerate cosmic expansion, but not enough to disrupt the galaxies or rip atoms apart. The difference between the predicted value and what we measure is beyond staggering. It's been described as the most catastrophic mismatch in the history of physics, a discrepancy of 1 followed by about 120 zeros. That's like predicting that a feather weighs as much as a mountain and finding out it barely tips a scale. This gap between theory and reality remains one of the great puzzles of modern science. Something, somewhere, is balancing the equation, but we don't yet know what. Perhaps there's a hidden mechanism that cancels most of the vacuum energy, leaving only a small remainder, just enough to fuel the universe's slow expansion. Or perhaps the energy of the vacuum isn't fixed at all, but changes over time, like a tide that rises and falls with ages of the cosmos. Some researchers suggest that as the universe grows, the vacuum energy might shift slightly, influencing the rate of acceleration in subtle, almost musical variations. For now, though, the simplest explanation is that dark energy is just what Einstein described more than a century ago, a constant property of space itself. Even when you take everything else away, the vacuum remains, and with it, this gentle energy. It doesn't come from matter, or from radiation, or from motion. It simply exists because space exists. Every cubic meter of the universe, no matter how empty, contains this faint uniform energy. Multiply that by the endless expanse of the cosmos, and you have the dominant force of creation. There's something poetic in the idea that the greatest power in existence is born from nothing. In human experience, nothing is a void, an absence, an end. But in physics, nothingness is an ocean of potential. The vacuum isn't a hole where things are missing. It's a field where possibilities flicker like candlelight. Out of that quiet sea of fluctuations, particles emerge, vanish, and sometimes leave behind echoes that shape everything else. Even the very forces that bind atoms together trace their origin to quantum fields humming invisibly in the void. To bring it closer to home, think about the space around you right now. Between the atoms of your body, between each breath of air, between Earth and the Moon, all of it is threaded by this vacuum energy. You are, in a very literal sense, surrounded by it. It is not something out there between galaxies. It's right here, filling every corner of reality. You are part of the same invisible ocean that stretches across the universe. Every heartbeat, every whisper, every quiet thought takes place within that expanding sea. Some scientists have tried to capture this energy directly in the laboratory. There's a small but famous experiment called the Casimir effect. When two metal plates are placed very close together in a vacuum, just a few atoms apart, they experience a faint attraction. It happens because the sea of vacuum fluctuations between the plates is slightly thinner than the sea outside them. It's as though the plates are pushed together by the pressure of nothingness itself. The effect is tiny, so small it can barely be measured, but it proves that the vacuum isn't empty. It has a structure, a presence, a quiet force all its own. When you think of the universe expanding, you might picture an explosion, a violent burst that throws everything outward. But the reality is the opposite. The universe expands not because of chaos, but because of stillness. It's the steady, uniform presence of vacuum energy that drives it. It's a force that asks for nothing, demands nothing, and yet it defines the future of everything. You could say that dark energy is the closest thing we've ever found to pure serenity, a calm power that doesn't act in bursts but through eternal patience. And perhaps that's what makes it so haunting. It reminds us that even in perfect silence, creation continues. Even in the quietest emptiness, something is at work, unseen and unstoppable. The same invisible pulse that pushes galaxies apart also flows through the space between your atoms. You are living inside the same fabric that breathes the universe wider every second. When you gaze up at the night sky, remember that what you see, the stars, the planets, the clusters of light, is only the visible embroidery on a far greater tapestry. The true engine of the cosmos lies in the unseen threads that connect it all, the energy that comes from nothing, yet makes everything possible. The next time you find yourself staring into the dark, don't think of it as empty. Think of it as full of quiet motion, full of potential, full of the soft hum that has shaped every moment since the beginning of time. In that endless, invisible calm, the universe continues to breathe, and so do you. When Albert Einstein first introduced his cosmological constant in 1917, he wasn't trying to create mystery. He was trying to preserve order. His equations for general relativity described how space and time are woven together, and how mass and energy bend that fabric. But those same equations told him something uncomfortable. The universe could not be static. It had to either expand or contract. At the time, that idea was nearly unthinkable. The stars seemed eternal, the heavens steady. So Einstein added a term to his equations, a small, gentle pressure that pushed outward, balancing gravity's inward pull. With that addition, the universe could remain perfectly still. He called it the cosmological constant. To him, it was just bookkeeping. He wanted a steady cosmos, and this new term gave him one. For a while, the idea held. Then, in 1929, Edwin Hubble aimed his telescope at distant galaxies and saw something that would change everything. The light from those galaxies was stretched, reddened, as if the galaxies themselves were fleeing into the distance. The universe wasn't static, it was expanding. In that moment, Einstein realized his balancing act was unnecessary. He reportedly called it the biggest blunder of his life. But history can be kind to blunders. decades later, that discarded constant would return, this time not as an error, but as an explanation. When astronomers discovered in the 1990s that the universe's expansion was speeding up, the cosmological constant suddenly made sense again. Einstein's tiny outward pressure, once thought to be a mathematical mistake, became the simplest way to describe dark energy. The universe, it seemed, was using his forgotten idea as its operating principle. To understand what this constant means, we can picture the universe as a vast, stretchy fabric. Every bit of space, no matter how small, carries a faint and uniform energy. This energy doesn't come from particles or radiation. It's built into the structure of space itself. When new space appears as the universe expands, more of that energy appears with it. It's not taken from somewhere else. It simply exists because space exists. And because energy curves space, the effect of this constant energy is to make the fabric stretch even faster. You can think of it as interest that compounds forever. The more space there is, the more of this energy there is, and the more it fuels expansion. There's no center, no edge, just a calm but unstoppable growth. It doesn't explode, it doesn't roar, it simply continues quietly, everywhere at once. Einstein could not have known what he had stumbled upon. He added the constant reluctantly, and later removed it even more reluctantly. Yet the deeper scientists looked into his equations, the more it seemed he had built a door into the universe's hidden future. That single symbol, representing a constant energy density filling all of space, might hold the secret to cosmic destiny. If this energy stays constant forever, the universe will keep expanding at an ever-accelerating pace. Galaxies will drift so far apart that their light will never reach one another again. In the far future, only the nearest stars will remain visible. Then even they will fade, leaving behind a dark, cold emptiness expanding faster than thought. If dark energy truly behaves as a constant, then this is the most likely fate. Not a violent end, but a quiet one. A slow dissolving of light into infinite night. But if dark energy isn't perfectly constant, if it can change even slightly, then the future could unfold differently. Some theories suggest it could weaken over time. If that happens, gravity might eventually slow the expansion, perhaps even stop it. Others propose that it could grow stronger, leading to a runaway scenario where the universe tears itself apart, atom by atom. These possibilities hinge on how the energy's pressure compares to its density, a relationship cosmologists describe through a single parameter, often called the equation of state. When the pressure is exactly equal to the negative of its density, the energy behaves like Einstein's constant. If it's slightly different, the outcome changes dramatically. We don't need symbols to grasp this balance. Imagine stretching a rubber sheet. If the stretch is steady and even, it's like the constant case, smooth, continuous. If the tension increases over time, the sheet might rip. If it decreases, the sheet might settle. Dark energy behaves much the same way, only on the scale of the entire universe. What makes the cosmological constant remarkable is its simplicity. It's just a number, an almost unimaginably small one, representing how much energy exists in every cubic meter of empty space. To give a sense of scale, if you filled a box a meter wide with this energy, it would weigh less than a grain of sand. Yet because the universe is so vast, that faint energy outweighs everything else combined. Stars, planets, galaxies. Altogether they account for less than a third of the universe's total energy. The rest belongs to this silent, uniform presence that fills the vacuum. It's a gentle kind of power, one that never clumps or gathers, never forms structures or radiates heat. It doesn't change when space stretches. It doesn't weaken as the universe grows. It just keeps doing what it does, pushing outward, endlessly, softly, forever. That steadiness is what makes it so mysterious. Every other form of energy we know diminishes over time. Light fades, matter spreads out, radiation cools. Only this energy endures unchanged, like the steady tone beneath the music of existence. There's a quiet irony in this. Einstein introduced the cosmological constant to keep the universe still, but in the end, it became the reason the universe moves without stopping. His desire for balance revealed the principle of expansion itself. It's as if he gave the universe a breath it can never quite release. If he could see the cosmos now, he might smile at the elegance of it. Not a blunder, but a symmetry. A universe that began in a blaze of creation continues to grow, not through chaos, but through a constant that holds everything together, even as it drives everything apart. A steady note playing beneath the cosmic song, and there's something almost comforting about that image. The same law that governs galaxies governs the space between your hands, the space between thoughts. The vacuum around you, invisible and quiet, carries the same tiny pressure that fills the vast reaches of the cosmos. You live within that constant, part of the same rhythm that Einstein glimpsed in his equations. Sometimes, the most extraordinary discoveries begin as mistakes. A small term added to an equation, a whisper ignored for decades, only to return as the central voice of creation. The cosmological constant reminds us that the universe doesn't need to be loud to be powerful. It only needs to be steady. So when you look up tonight and feel the stillness of the stars, remember that the stillness is an illusion. Beneath it, space is expanding, silently, perpetually, guided by a constant written into the universe itself. A constant so faint that you'll never feel it, yet so vast that it defines everything you will ever see. Einstein once tried to hold the cosmos in place. In doing so, he may have given it the key to eternity. Even now, after decades of observation, dark energy remains more question than answer. The simplest explanation, Einstein's constant energy of empty space, fits the data beautifully, but it might not be the whole story. Some scientists suspect that what we call dark energy could be something more alive, something that changes over time, a kind of invisible field that fills the universe, not fixed but flowing, like a breeze that never stops. This idea is called quintessence, the fifth essence beyond earth, air, fire, and water. It's a name borrowed from ancient philosophy, when the heavens were believed to be made of a pure, eternal substance. In a way, modern physics has returned to that dream, searching for a fifth element that could explain why the cosmos continues to stretch. To understand quintessence, imagine the universe as a landscape of hills and valleys made not of matter, but of energy itself. In this view, space is not a blank stage, but a living field that can roll and shift. Over cosmic time, the field might slowly move, changing the strength of dark energy as it does. In the early universe, it could have been weaker, allowing galaxies and stars to form. Later, it might have grown stronger, driving the acceleration we see today. If that's true, the fate of everything depends not on a constant, but on the slow evolution of this invisible sea. Physicists describe the behavior of dark energy using a single parameter known as the equation of state. It compares the pressure the energy exerts to the amount of energy it holds. If the outward push is exactly equal to the negative of its density, then dark energy behaves like Einstein's cosmological constant, perfectly steady. But if that ratio shifts even slightly, the character of the universe changes. When the pressure is less negative, the energy weakens over time. When it's more negative, the energy grows stronger, perhaps infinitely strong. We don't need numbers to grasp what that means. Think of a balance between two forces, gravity pulling inward and dark energy pushing outward. If the push matches a steady rhythm, the universe expands calmly. If it weakens, gravity might someday begin to slow the expansion. But if it grows stronger, the expansion will accelerate until it tears apart everything that exists. That extreme case is known as phantom energy, a term that feels almost too poetic for something so ominous. Quintessence and phantom energy are two sides of the same question. Is dark energy constant, or is it evolving? We don't yet know. The evidence we have from supernovae, the cosmic microwave background, and large-scale galaxy surveys all point to a value very close to steady. Close enough that, if it changes at all, the change is slow and subtle, unfolding over billions of years. But even a small drift could rewrite cosmic history. If dark energy is dynamic, it might explain why the acceleration began only recently in cosmic terms. For most of the universe's life, gravity dominated, shaping galaxies and clusters from the primordial chaos. Then, only a few billion years ago, something shifted. The balance tipped, and the acceleration began. It was as if the universe had been waiting, slowly gathering breath, before letting the expansion loose again. Quintessence provides a possible reason for that timing, an energy field whose strength grows over time, finally overcoming the collective pull of matter. Some models even suggest that this field could oscillate, waxing and waning like the tide. In one era, the expansion might speed up. In another, it could slow down. The cosmos might breathe in cycles, each one lasting longer than the age of all human civilization combined. In that vision, the universe is not a machine winding down, but a living rhythm, a pulse that beats across eternity. The idea of a changing dark energy also offers a subtle hope. If the energy grows weaker someday, the universe might not end in a lonely freeze. Instead, expansion could ease into balance, leaving behind vast islands of galaxies still bound together, their light fading gently but never fully extinguished. In that gentler fate, the cosmos would not vanish into nothingness, but drift into quiet equilibrium, a stillness that feels almost merciful. And yet, the phantom possibility lingers, that the pressure could grow instead of fade. If it does, the universe's acceleration would increase without bound. Galaxies would separate faster and faster, until even atoms could no longer hold together. In that far-off future, the very fabric of space-time might rip itself apart. The end would not come as fire or ice, but as dissolution, a slow unravelling of reality. It's a haunting image, existence stretching beyond its limits, undone by its own expansion. For now, all we can do is measure. Every year, astronomers refine their instruments, seeking the faintest clues to whether dark energy's strength has changed. They watch ancient supernovae whose light has travelled for billions of years, comparing them to younger ones in nearer galaxies. They map the cosmic web, tracing how clusters of matter have formed and drifted. From these observations, they try to read the pulse of the universe, to learn whether that pulse is quickening or steady. Each new survey, from the Dark Energy Survey in Chile to the Euclid mission orbiting Earth, gathers more light, more data, more whispers, from the edge of time. And with every new data set, the picture remains largely the same. Dark energy behaves for now like a constant, but science thrives on the space between for now and forever. Perhaps in another billion years the universe will reveal a new tempo. Perhaps the equation of state, that delicate balance between pressure and energy, will drift slightly, signalling that the cosmos is changing its tune once again. Or perhaps it will stay the same for all eternity, an unbroken rhythm that outlasts every star. Whichever is true, there's something deeply human in the search. We look up at a sky filled with light from galaxies that no longer exist, and we try to understand what drives their fading. We measure the unmeasurable, listen for a hum that may never stop. We call it dark energy because it hides from us, but the truth is, it's also a mirror. It shows how small we are and how far our curiosity can reach. The ancients imagined quintessence as the purest substance, the breath of the heavens. They believed it surrounded the stars and filled the void. Now, in our modern way, we've returned to that vision, not out of myth, but through mathematics and observation. And yet, beneath the equations and the instruments, the feeling is the same: awe, wonder, and the quiet realization that what we call nothing might be the most powerful thing of all. So when you gaze into the dark between stars, know that you're not looking into emptiness. You're looking into the source of motion itself, the invisible tide that carries galaxies apart, the silent energy that shapes time. Whether it's constant or changing, gentle or fierce, it's the same breath that fills every corner of the cosmos, the shape of an unknown force, drawn not with light or matter, but with the endless patience of the universe itself. Among all the possible futures that scientists have imagined for the universe, there is one that feels almost like a ghost story told by the cosmos itself, a tale where the universe does not fade into silence or fold back on itself, but instead unravels completely. This possibility arises from the idea that dark energy might not be steady or gentle, but wild, stronger with time, feeding on expansion the way a flame feeds on air. This is the realm of what physicists call phantom energy. The name sounds poetic, and it is, but it also carries a quiet dread. Phantom energy represents a version of dark energy so powerful that it could, one day, pull everything apart, not just galaxies or atoms, but the very fabric of space-time itself. To understand why this idea is so unsettling, we can return to that balance between pressure and energy. When dark energy's pressure equals exactly the negative of its energy density, it behaves like Einstein's cosmological constant, a steady, eternal presence. But if the pressure becomes even more negative, if it pushes harder than its density should allow, then the expansion of the universe doesn't just accelerate, it accelerates without limit. The ratio between the two, which cosmologists express through a single parameter called W, becomes less than -1. We don't need to write the symbol, it's enough to know that when this number drops below that boundary, the universe's calm breath turns into a storm. In such a universe, space doesn't simply grow, it tears. Every moment of time stretches the distance between galaxies a little more than the moment before. Gravity, that patient sculptor of stars and worlds, begins to lose its grip. First, galaxy clusters drift apart, their connections severed by expansion. Then, the galaxies themselves start to come undone. Stars that once circled together are left to drift alone, cut off from their neighbours. As the acceleration grows more violent, even solar systems like ours would not survive. The bond between the Sun and Earth would weaken, the invisible threads of gravity stretched until they snap. Planets would drift away, the night sky emptied of constellations. But the story doesn't stop there. If phantom energy continues to strengthen, it eventually begins to unmake the smaller and smaller structures of reality. Stars would disintegrate, their material pulled apart faster than nuclear forces can hold it together. Then the same fate would come for atoms. The electric bond between electrons and their nuclei, unable to resist the expansion of space itself. Even the particles inside atoms, bound by the strongest forces known, would find no refuge. The expansion would reach them too. At that point, space-time would be stretched so violently that even the concept of distance would lose meaning. Everything, matter, energy, light, time, would dissolve into a single, endless wave of expansion. This catastrophic ending has a name that sounds almost too soft for what it describes. The Big Rip. It's not a definite prediction, just one of several possible fates. But it carries a strange kind of fascination. Unlike the slow freeze that most scientists expect, the Big Rip would arrive suddenly, in cosmic terms, not over trillions of years, but perhaps in tens of billions. For the first 9/10 of its lifetime, the universe would look almost normal. Galaxies would continue to drift, stars would shine, life might go on. And then, as phantom energy gathered strength, everything would begin to accelerate toward oblivion. The closer things became, the faster they would move apart. The fabric of reality would tear in a crescendo of expansion. It would be the quietest apocalypse imaginable. No explosion, no fire, just the final vanishing of structure. Though this sounds terrifying, it also reminds us of the strange gentleness of cosmic laws. Even destruction in the universe often comes with grace. The Big Rip, if it ever happens, would not feel like violence. From the inside, every observer would see distant galaxies rushing away faster and faster until there was nothing left to see. Then, in the final moments, the very space around them would dissolve. The process would be smooth, inevitable, and silent. A final exhalation from a universe that had been breathing for billions of years. For now, there is no sign that we are headed towards such an end. The data we have show that dark energy behaves almost exactly like a cosmological constant. The phantom scenario remains only a possibility, a shadow cast by our uncertainty about what dark energy truly is. But the idea itself serves a deeper purpose. It reminds us that the laws of the universe, though written in equations, still hold room for imagination. They remind us that even the calmest of forces might hide extremes we cannot yet foresee. And perhaps beneath its grim surface, the phantom idea carries a kind of strange beauty. It's a vision of a universe that does not fade or collapse, but transforms. A reality that expands so far that boundaries themselves no longer exist. In that final act, everything that was separate becomes one again, not through fire or ice, but through endless distance. It's a poetic symmetry to the Big Bang. Where one moment birthed all space and time, another might dissolve them, returning the cosmos to a state beyond definition. Physicists continue to study what such a scenario would mean. Could quantum effects prevent the final tear? Could new physics emerge before that moment arrives, stabilizing the expansion? Some even wonder if the Big Rip, rather than an end, could be a doorway. If the fabric of the universe truly tears, could something new slip through? A new universe, born from the remains of the old? It's speculation, but not without precedent. The universe has reinvented itself before. From the chaos of the Big Bang, order arose. From the collapse of stars, new stars were born. Perhaps even from a cosmic rupture, creation could begin again. When you imagine this possibility, don't think of it as horror. Think of it as transformation. The universe exploring its limits, reaching as far as existence can stretch. The phantom's whisper isn't a scream of destruction. It's the echo of curiosity, the same impulse that drives us to look up and wonder. After all, the only reason we know of such possibilities is because we dare to ask how the universe works, and to follow the answer wherever it leads. In the quiet night, it's easy to forget how dynamic the cosmos really is. Everything around you feels stable, permanent, but on a cosmic scale, nothing is truly still. The same invisible energy that stretches galaxies apart is at work even here, between you and the walls of the room, between your heartbeat and the next. It's so faint you'll never feel it, yet it shapes the destiny of everything. Whether that destiny is an eternal expansion or a final unravelling, we don't yet know. But there is peace in that not knowing. The mystery itself is the melody that keeps the universe alive. So if one day you find yourself awake beneath the stars, let your thoughts drift to the vastness above. Somewhere, far beyond the reach of any telescope, galaxies are already moving apart faster than light, carried away on a current that never slows. That current is the whisper of dark energy, the same whisper that will decide how every story ends. Maybe it will fade, maybe it will grow, maybe it will tear the heavens open. Whatever it becomes, it is the quiet pulse that ties every atom, every planet, every dream to the same expanding fabric. A phantom, yes, but one that speaks softly, endlessly, through the widening silence of the night. If you could watch the universe from an impossible distance, not from inside one galaxy, but from beyond them all, you would see something that looks like a slow dance between two invisible partners. One partner pulls everything inward, patient, constant, and familiar. That's gravity. The other partner moves in the opposite direction, steady, soft, but just as relentless. That's dark energy. Their dance is not one of chaos but of delicate balance, each shaping the rhythm of cosmic history. Gravity has always been the sculptor. It gathers dust and gas, presses them into stars, binds stars into galaxies, and weaves galaxies into clusters that stretch like luminous lace across the blackness of space. Without gravity, there would be no suns to shine, no planets to orbit, no warmth, no life. For billions of years, it has been the quiet artist behind every form we know. But dark energy plays a subtler role. It doesn't pull, it pushes. It doesn't build, it separates. It acts everywhere at once, not from within matter, but from the very emptiness between it. If gravity is the thread that stitches the cosmos together, dark energy is the gentle tug that keeps the fabric from tightening too much. The two are opposites, yet together they define everything that happens, from the birth of stars to the fate of the entire universe. On the small scale, gravity is stronger. Inside galaxies, it reigns supreme, holding stars in their spiraling dance. Even across galaxy clusters, regions hundreds of millions of light-years wide, gravity's pull overcomes the slow, outward drift of space itself. But on the grand scale, beyond those clusters, dark energy begins to dominate. It's as if the universe has two laws, one that rules the near and another that rules the far. Up close, attraction wins. Across the vastness, separation takes over. Astronomers see the evidence of this balance everywhere they look. When they measure the motions of galaxies, they find that those within the same cluster move together, held tight by their mutual pull. But when they compare distant clusters, they discover that the space between them grows wider every year. The farther apart two clusters are, the faster that space expands. The pattern is consistent and precise, a cosmic geometry written across billions of light years. You could imagine it like ripples on a pond that have been frozen mid-wave, each crest held apart by the universe's breath. Gravity tries to pull the water back, but the wave has already formed. The surface continues to stretch outward. That's what cosmic expansion looks like when you step far enough back. It's not an explosion racing through space, but a quiet swelling of the space itself. And though it sounds like conflict, gravity versus dark energy, it's more of a conversation, one that has shaped the cosmos since its beginning. In the early universe, matter was dense, hot, and close together. Gravity dominated completely, slowing the initial expansion that followed the Big Bang. Over time, as the universe grew and matter spread thinner, gravity's grip weakened. Dark energy, constant and patient, began to take over. Around 5 billion years ago, long after our sun formed but long before our distant descendants will vanish, the balance shifted. The push began to win. The expansion stopped slowing and started to speed up again. Since then, dark energy has become the quiet conductor of cosmic destiny. It dictates how galaxies drift apart, how light stretches as it travels, even how time unfolds on the larger scales. And yet, this dominance is not violent. It's graceful, almost tender. The stars don't feel it. The galaxies don't notice it. Only when you look across the immensity of space does the pattern reveal itself. The slow divergence of everything from everything else. The contrast between these two forces tells a story that feels familiar to us in a very human way. We understand the pull of gravity because we live under it. We feel it every moment of our lives, an anchor keeping us grounded. But we also know the feeling of drift, of moving away, of separation. Dark energy is that drift made cosmic, the gentle inevitability of distance. It's the reason that even light, which travels faster than anything we know, eventually loses the race against the expansion of space. The farther it travels, the more it stretches, the fainter it becomes, until one day it fades completely beyond reach. Scientists describe this relationship with precision, but you can understand it without numbers. Gravity's strength decreases with distance. It weakens as objects move apart. Dark energy's strength, however, stays the same everywhere. It doesn't fade with distance. The more the universe expands, the more of this energy there is, because new space means new energy. Imagine a field of grass where every blade grows taller at exactly the same rate. The farther you look, the more grass you see, and the faster the whole meadow seems to rise. That's how the expansion of space behaves under dark energy, not from a centre, but everywhere, evenly. There's something almost philosophical in this cosmic balance. Gravity gathers, dark energy releases. One creates structure, the other creates freedom. One is the force of unity, the other is the force of solitude. Yet without both, the universe could not exist as it does. If gravity had won completely, the cosmos would have collapsed into a single dense point, an eternal night of compression. If dark energy had dominated from the beginning, galaxies would never have formed. Everything we know, every star, every breath, every thought, depends on this fragile equilibrium that allows the universe to both hold together and let go. And that balance, like all balances, may not last. Dark energy's push continues to grow stronger as the universe expands. Gravity tied to matter that thins out with every passing eon will continue to weaken. One day, perhaps, gravity will rule only within small islands of galaxies, while dark energy rules the seas between them. The cosmic dance will slow, the partners drifting apart, the music fading into distance. Still, for now, we live in the moment between those extremes. The stars still shine. Galaxies still gather in clusters, bound by the same pull that holds the moon to Earth. The night sky above us is full of that delicate balance. Light and dark, pull and push, creation and release. And in that balance, there is beauty. So tonight, as you imagine the universe stretched across its vast ocean of darkness, picture those two forces, gravity and dark energy, not as enemies, but as dancers who have shared the same floor since the beginning of time. One draws close, the other opens space. Together they create the rhythm of existence itself. And yet, every dance must end, even one measured in billions of years. The moment will come when one partner steps back, when the harmony becomes adrift. The balance will break, softly, inevitably. The universe will keep expanding, and gravity will yield. That's the quiet truth of this cosmic waltz, that beauty and loss have always been intertwined, written into the same steps. And even as the galaxies continue to drift apart, the pattern they leave behind, this gentle battle of forces, will remain the most graceful thing the cosmos has ever done. It's easy to imagine galaxies as travellers, racing through a dark, empty void, little boats drifting across an infinite sea. But that image is misleading. The galaxies are not moving through space, the space between them is growing. The difference is subtle, but profound. Nothing is sailing away. Instead, the ocean itself is expanding, carrying the boats along with it. That is the quiet truth of cosmic acceleration. Space doesn't just contain the universe, it is the universe, and it's changing under our feet. To understand this more gently, picture a loaf of bread rising in the oven. The dough represents space itself, and the raisins inside are galaxies. As the dough expands, the raisins move apart, though none of them are moving on their own. From the perspective of any single raisin, all the others seem to be fleeing, yet no raisin is special, no raisin is the centre. The expansion happens everywhere at once, uniform and patient. It doesn't begin from a point and spread outward like an explosion. Instead, every point expands simultaneously, so that from any location the universe looks the same. This expansion is what astronomers call the metric expansion of space. But we don't need that phrase to feel its meaning. It's the gentle stretching of distance itself. The measurement between things growing, not because things move, but because the ruler you use to measure them is slowly lengthening. Over billions of years, this stretching reshapes everything on the largest scales. Galaxies drift farther apart, clusters loosen, and light travelling through the universe finds its path lengthened as the fabric expands beneath it. When a beam of light leaves a distant galaxy, it carries a certain colour, a certain rhythm. As it travels, the space it moves through stretches, and so does the light itself. Its wavelength becomes longer, its colour shifts toward red. This is why astronomers say that light from distant galaxies is red-shifted. It's not that the light changes its mind mid-journey, it's that the universe changes the road beneath it. The greater the distance, the greater the stretching, and the older the light. It's like hearing a song played through a slowly bending record. Each note drawn out, deeper, softer, until the melody feels timeless. This stretching has strange consequences. Because the universe is expanding faster and faster, there are galaxies whose light will never reach us no matter how long we wait. They are already moving away faster than light can travel through space. It isn't that they are breaking the cosmic speed limit, it's that space itself is carrying them beyond the reach of light. Astronomers call this boundary the cosmic horizon, the distance beyond which events can never influence us. Every second, more galaxies slip across that horizon, disappearing not by fading, but by being carried away into a region of space we can never see again. Think of that for a moment. Entire galaxies, each containing hundreds of billions of stars, vanishing into a distance that grows faster than light. Whole histories are drifting away from us, their stories written in light that will never arrive. In the deep future, countless civilizations might exist beyond that horizon, unreachable, invisible, lost to us forever. The night sky will grow emptier not because the stars die, but because the space between us expands faster than their light can cross. It's as if the universe is turning down the dimmer switch of time, one galaxy at a time, and yet the local world remains unchanged. Here, gravity still holds us together. The Earth still circles the Sun still circles the Milky Way, and the Milky Way itself remains bound to its neighbouring galaxies by an invisible thread of gravity stronger than the pull of cosmic expansion. It's only across vast distances, tens or hundreds of millions of light years, that dark energy's hand becomes stronger than gravity's grasp. The universe has divided itself into realms, small islands where gravity rules, surrounded by an ever-widening ocean where dark energy reigns. The quiet power of this idea is that it changes how we think about motion. In ordinary life, when something moves, it travels through space. But on a cosmic scale, motion is an illusion. Nothing is travelling outward. Instead, the space between things is growing. Even the speed of light, the ultimate constant, is powerless against this change, because it isn't racing through a fixed stage and the stage itself is swelling. Light moves as fast as anything can move, but if the space it crosses doubles while it travels, the destination slips away faster than it can arrive. It also changes how we think about time. The stretching of space stretches time along with it, because the two are inseparable, parts of the same fabric. When we say space-time, we mean exactly that. Not two separate things, but one woven cloth. As the cloth expands, so does the rhythm of the universe. The seconds between events in the farthest galaxies grow longer. The intervals between cosmic heartbeats widen. Locally, our clocks tick normally, but across the vastness of the cosmos, time itself is under tension, like a rubber band slowly drawn tight. In Einstein's picture, this happens because energy and matter tell space-time how to curve, and that curvature tells matter how to move. When the energy of the vacuum, dark energy, fills every corner of space, it changes the curvature everywhere at once. The result is a global stretching that no single object can escape. We can't see it happening directly, but we feel it in the redshift of light, in the dimming of distant supernova, in the quiet evidence that everything is being carried gently apart. It's tempting to feel small in the face of such vast motion, but there's also something deeply peaceful in it. The expansion isn't chaotic, it's ordered, smooth and steady. It doesn't destroy the structures gravity has already built, at least not yet. It simply gives them room to drift, space to breathe. It's the universe's way of ensuring that nothing becomes too crowded, that everything has its distance. Sometimes, when you look up at the stars and imagine their light travelling for billions of years to reach you, you are seeing this expansion in action. The starlight that touches your eyes tonight has been stretched by the universe itself. Every photon carries the story of that journey, the lengthening of space, the deepening of time. In that sense, you're not separate from the expansion, you're part of it. Your atoms, your heartbeat, your very thoughts unfold within the same fabric that grows between the galaxies, and even though the galaxies drift farther away, there's a strange unity in this motion. Everything moves together, in sync, as part of one great unfolding. The universe isn't breaking apart, it's breathing. A slow, patient exhalation that carries stars and light and time itself outward into the infinite. So when astronomers say that even light cannot outrun the expansion of space, it's not a warning, it's a kind of lullaby. It means that the cosmos is larger, softer, and more interconnected than our minds can easily hold. Every second, new space appears, new distance unfolds, new moments are born. The universe isn't running away from us, it's simply becoming more of itself, endlessly, quietly, beautifully. If you could listen closely enough, the universe would have a rhythm, not a sound exactly, but a tempo, a slow stretching of moments, a cosmic heartbeat that changes with the shape of space itself. The farther the universe expands, the more time seems to loosen, like a thread drawn gently through an endless fabric. The seconds still pass here, in your room, with their familiar rhythm, but across the vast distances between galaxies, those same seconds lengthen, becoming slightly more spacious, slightly more distant from one another. The expansion of space stretches time too, because space and time are not separate things. They are two notes of the same song, what physicists call space-time. And when one expands, the other deepens its tone. Einstein once described gravity not as a force pulling downward, but as a curve in space-time created by mass and energy. The more massive an object, the deeper the curve. A star, a planet, even you. Each bends the fabric around you ever so slightly. And because time flows along that same fabric, gravity affects time as well. Where gravity is strong, time slows down. Where gravity is weak, time runs faster. This isn't just theory. We've measured it. A clock placed at the bottom of a mountain ticks more slowly than one at the top. The difference is tiny, only a few billionths of a second, but it's real. GPS satellites circling Earth have to account for this time dilation, otherwise their navigation systems would slowly drift out of sync. Time itself depends on where you stand in the universe. Now imagine scaling that idea up to the cosmos. If gravity can stretch or squeeze time on the scale of mountains, what happens on the scale of galaxies, of billions of light years? In regions filled with matter, stars, dust, planets, gravity keeps time anchored, steady, compact. But in the vast voids between galaxies, where dark energy dominates, time expands along with space. The seconds there are longer, more diluted, as if the ticking of the cosmic clock slows the farther you move from the pull of mass. It's hard to feel this directly because we're so small within the grand design, but the evidence is all around us, written in light. When we look at distant galaxies, we're also looking into the past. Not because light moves slowly, but because the light itself has travelled through stretching space and stretched time. The rhythm of that light has changed, its waves drawn longer as the universe expanded during the journey. In this sense, every photon is a clock, and its wavelength a record of time's expansion. The redder the light, the older the time it comes from. Think of a second near a black hole, the densest, most extreme form of gravity we know. To an observer far away, that second can appear as hours, days, or even years. The deeper the gravity, the slower the clock. Now think of the emptier space, where gravity has almost no influence. There the opposite happens. Time flows freely, perhaps faster, perhaps lighter, as if it's stretching its limbs in the quiet. The universe is filled with both extremes, places where time is trapped and places where it drifts effortlessly, and in between them, a balance, fragile and precise. In that balance lies the story of dark energy. As the universe expands, more and more regions fall under dark energy's rule. Matter becomes sparser, gravity weaker, and time more elastic. Cosmic acceleration isn't just a stretching of space, it's a stretching of duration itself. Each moment, from the birth of a star to the flicker of thought in a human mind, takes place within this shifting rhythm. The tempo of the universe changes as it grows. For us it's imperceptible. We measure time in heartbeats, in breaths, in sunrises and shadows. But the universe counts in scales beyond comprehension, in billions of years, in distances so great that light takes entire epochs to cross them. On those scales, the expansion of time becomes visible. Galaxies move apart and the intervals between cosmic events grow longer. 1 billion years in the early universe might have contained a frenzy of star birth, while 1 billion years now feels more languid, more spacious. The music of creation is slowing its pace. This stretching of time also carries philosophical weight. If time can flow differently depending on where you are or how the universe evolves, then what does it mean to say that two events happen at the same time? In the language of relativity, simultaneity is not universal. There is no single cosmic clock keeping time for everyone. Every observer, every galaxy, every atom measures its own version of now. When you gaze at a distant star, you aren't just looking into space. You're looking across time into a different tempo of existence. The universe is a grand orchestra of clocks, all ticking at their own rates, all part of one cosmic harmony that never quite resolves into a single beat. And yet, this isn't chaos. There's a strange order in the way time stretches and folds. The equations that describe it are simple in form, though deep in meaning. They tell us that as space expands, the scale of time expands with it. The ratio remains fixed. Space and time always grow together, like dancers whose steps are perfectly synchronized, even as the dance floor itself widens around them. It's a partnership so complete that we cannot imagine one without the other. Without space, there is nowhere for time to move. Without time, space cannot change. Some scientists have begun to wonder whether dark energy, by stretching space, is also changing the very nature of time. Could it be that the acceleration we see is, in part, a reflection of time itself speeding up? If every moment were becoming slightly shorter than the one before, would we notice? Or would our clocks, our thoughts, our very cells adjust without us ever realizing? The question is more poetic than practical, yet it carries an unsettling beauty. Perhaps the universe is not expanding into more space, but into more time. If that sounds abstract, think of it this way. Every breath you take adds to the age of the universe, but that age is not measured against some fixed background. The stage beneath you, time itself, is stretching as you move through it. You're both part of the expansion and the measure of it. You are, in your own quiet way, helping the universe grow older. At some point, perhaps far in the future, the tension between gravity and expansion will reach its limit. The fabric of space-time can stretch only so far before it becomes thin enough that structures begin to unravel. Maybe it will be trillions of years from now, maybe longer. Stars will fade, galaxies will dissolve, and time, that loyal companion of motion, will drift into stillness. It won't end abruptly, it will dissolve, just as the last light fades from a dying star. For now, though, the balance holds. Time stretches, but it also flows. Space grows, but it still carries us gently within it. And somewhere in that slow rhythm between the pull of gravity and the push of expansion lies our brief existence. Each moment you live is a small note in that vast cosmic melody, a reminder that even as the universe expands beyond comprehension, it still keeps time with you. If you could look into the future of the universe, not a century or a million years ahead, but billions upon billions, you would see a slow, endless parting. Galaxies that once filled the night sky with scattered jewels would drift so far away that their light could never reach one another again. The stars would continue to burn for a while, some for billions of years, others for just moments by cosmic standards, but eventually even they would fade. The cosmos would not die in fire or collapse in fury, it would die by growing quiet. The universe would not end quickly, it would simply forget how to shine. This is the story scientists call the Big Freeze, the most likely fate of all things. In this scenario, the expansion of the universe never stops. It continues forever, powered by dark energy's steady push. Galaxies drift apart until, to an observer in one galaxy, the rest of the universe disappears beyond the cosmic horizon. No new light arrives from other worlds. The universe becomes an archipelago of isolation, each galaxy a solitary island adrift in an ocean that grows wider every second. At first, within those islands, life goes on. Stars keep burning, planets keep circling, black holes keep swallowing stray matter. But even stars are not eternal. The most massive burn brightly and die young. Smaller ones burn slowly and fade into embers. As the eons pass, fewer and fewer stars are born. Gas, the raw material of creation, becomes scarce. Gravity still tries to gather what remains, but dark energy keeps pulling it apart. The night grows darker, not from sudden loss, but from slow exhaustion. After 1 trillion years, most of the visible stars will be gone. Only red dwarfs, faint, long-lived sun, will remain, glowing with a dull crimson light. Eventually, even they will fade into black dwarfs, cooling in the silence. The galaxies will become dim shadows of their former selves, their brilliance reduced to whispers of heat. By then, time will have stretched so far that a second will mean nothing. The intervals between cosmic events will be so long that no mind could ever hold them. Then comes the age of black holes. As the last stars die, the universe will be ruled by these invisible giants, the remnants of once great suns. They will persist for unimaginably long periods, perhaps 10 to the power of 100 years. Even they, however, will not last forever. According to quantum theory, black holes slowly lose mass through a process known as Hawking radiation, a faint evaporation at the edge of nothingness. Over time, they too will vanish, leaving behind only empty space and a thin mist of low-energy particles. By that distant epoch, there will be no more heat differences, no more light or motion, only equilibrium. The cosmos will have reached what physicists call heat death. It sounds dramatic, but it's more like a sigh than an explosion. Every star, every atom, every flicker of energy will be spread so thinly that no new events can occur. Entropy, the measure of disorder, will have reached its peak. The universe will no longer change because there will be nothing left to change. In that endless stillness, time itself will lose meaning. When nothing happens, what does it mean for time to pass? Seconds, years, and centuries all rely on movement, on change, on something marking the difference between before and after. In a universe without light or life, there would be no way to tell that time still flows. Perhaps it would continue, stretching into infinity, or perhaps it would dissolve, like a wave that finally merges with the sea. The Big Freeze may sound tragic, but there's a strange peace in it too. The universe began in blinding heat, a storm of energy too violent for structure, too bright for form. It took billions of years of cooling for stars to ignite, for planets to form, for life to dream. The same cooling that once allowed beauty to emerge will one day bring stillness. It's not a punishment, only the natural exhalation of a universe that has been breathing for 15 billion years. It's the quiet that follows the final note of a symphony, not silence, but fulfillment. And yet scientists still explore other endings. There is the Big Crunch, an older vision from before we knew about cosmic acceleration. In that version of the story, gravity would one day overcome expansion, pulling the universe back inward. Galaxies would collide, stars would merge, and everything would end in a fiery collapse, a mirror image of the Big Bang. But the discovery of dark energy made that future unlikely. The expansion isn't slowing, it's racing. The universe is not preparing to fall, it's preparing to drift. Then there's the darker, more dramatic cousin of the Big Freeze, the Big Rip, a fate born from the idea of phantom energy. In that version, dark energy's strength increases with time until even atoms cannot resist it. Galaxies are torn apart, stars shredded, planets ripped from their orbits. In the final moments, even the molecules inside your body would separate, the space between particles stretched beyond recognition. And then, the fabric of space-time itself would tear. A cosmic unravelling. It's a frightening picture, but perhaps only a metaphor, a reminder of how fragile balance really is. Between these fates, the crunch, the freeze, the rip, lies a question deeper than physics. What does it mean for something to end? Is death the absence of change, or just a new kind of order? The universe may not see these questions as we do, but we are part of it, and so our wondering becomes part of its story. When we ask about the end of time, we're really asking about the meaning of our own brief moment within it. If you listen closely to the night sky, you can almost feel this slow farewell unfolding already. The faint galaxies we see through telescopes today may no longer exist by the time their light reaches us. We are witnessing ancient events, explosions and births from billions of years ago, replayed across time. The cosmos is not static, it's a moving picture whose frames grow farther apart with every breath. The light from distant stars travels through space that stretches as it moves, like a song echoing in a hall that keeps expanding. By the time it reaches us, the melody is softer, slower, tinged with red. And so, every time you look up, you're watching a long goodbye. The stars are still there, but their light is aging as it travels, dimming gently before it ever reaches your eyes. The universe is not dying fast, it is forgetting slowly, one wavelength at a time. There's something strangely comforting in that thought. It means that even as everything moves away, it does so gracefully. The galaxies don't shatter, they drift. The stars don't vanish, they fade. The end, if it comes, will not be a scream but a sigh. The same quiet patience that brought the universe from chaos to order will one day carry it from brightness to rest. And perhaps, in that far future when the last light flickers out, something new will begin again, a quantum fluctuation in the eternal dark, a spark in the quiet sea of nothingness. Maybe that spark will expand, warming, brightening, until it becomes another universe, another chance for stars to shine and eyes to open. Maybe creation and forgetfulness are simply two sides of the same breath. For now, though, the universe still glows, stars still burn, planets still orbit, and on one small world in the corner of one small galaxy, there are minds that can look up and wonder why. We are the temporary witnesses of eternity's slow unfolding, and as the light of the cosmos continues to stretch and fade, we remain part of its memory, the fleeting awareness within the long goodbye of everything. To understand something as vast and silent as dark energy, humanity has had to invent new ways of listening. We cannot see it, we cannot touch it. It leaves no direct trace in the light that reaches our telescopes, and yet its influence is everywhere, written into the way galaxies drift, the way starlight bends, the way the entire universe expands. To map this invisible presence is to attempt the most delicate cartography imaginable, to chart the shape of the unseen. Astronomers do not use brushes or ink for this map. They use light, the faintest, oldest light in existence. Every photon that reaches Earth carries a record of how space has stretched since it began its journey. The farther that light has travelled, the more the universe has expanded, and the redder the light has become. By comparing the colour and brightness of thousands of distant galaxies and exploding stars, scientists can measure the changing rate of expansion across time. In a sense, they are watching the universe grow old, one wavelength at a time. One of the great efforts in this cosmic cartography is the Dark Energy Survey, a collaboration that used a powerful telescope in Chile to scan a vast portion of the southern sky. For 6 years, astronomers took deep images of hundreds of millions of galaxies, measuring not only where they were, but also how their shapes had been subtly distorted. That distortion, tiny and almost imperceptible, comes from gravitational lensing, the way light bends as it passes through the gravity of massive structures. It is as if invisible fingers have brushed across the starlight, bending its path before it reaches us. By studying those faint bends, researchers can map the unseen mass of the universe, both dark matter, which pulls, and dark energy, which pushes. Every image tells a story of balance. The clustered galaxies show where gravity is still strong. The empty voids between them show where dark energy rules. When these patterns are compared across billions of years, a rhythm emerges. A universe once dominated by attraction, now guided by repulsion. It's not an easy rhythm to hear. It takes vast amounts of data, careful corrections, and endless patience. But when the melody is finally revealed, it's unmistakable. The tempo of cosmic expansion is accelerating. More recently, the DESI project, the Dark Energy Spectroscopic Instrument, has begun creating an even more detailed map. It doesn't just take pictures of galaxies, it measures their light with exquisite precision. By spreading that light into its rainbow of wavelengths, scientists can tell exactly how far each galaxy is and how fast it is moving away. Over time, these measurements will create a three-dimensional picture of the universe, not just where things are now, but where they were billions of years ago. The result will be a time-lapse of cosmic history, showing how dark energy's influence has changed across epochs. Then there is Euclid, the European Space Agency's new satellite now floating far from Earth. It peers into the deep darkness, looking for the subtle patterns that dark energy leaves behind. It measures how galaxies cluster, how space warps, and how the cosmic web, that vast network of filaments connecting everything, slowly loosens its grip. With each new survey, our picture of the universe becomes sharper, yet somehow more mysterious. Every answer seems to whisper another question. And of course, above all of these is the James Webb Space Telescope, with its golden mirrors unfolded like a celestial flower, collecting light from the first galaxies ever formed. Webb can see farther back in time than any instrument before it, reaching the era when the universe was only a few 100 million years old. By studying how those ancient galaxies formed and moved, astronomers can learn how quickly dark energy began to influence the expansion. In this way, each telescope becomes a listener to the universe's most distant echoes, an ear pressed to the heartbeat of creation itself. What's remarkable is that all of these experiments depend not on finding dark energy directly, but on seeing what it does to everything else. We watch the way galaxies arrange themselves, the way light bends, the way empty space grows. Dark energy is like wind on the ocean, invisible, but revealed by the waves it leaves behind. And even as we build better instruments, we are reminded that what we seek may never be fully visible. It may be something woven into the nature of space-time itself, not a substance to detect, but a property of existence. Still, we try. Each survey adds another layer to the cosmic map. The result is not a picture you can hang on a wall, but a mathematical landscape, a three-dimensional map of light and shadow stretching across billions of years. In that landscape, we can see how galaxies cluster, how they drift, how they vanish beyond our horizon. We can see how the speed of expansion has changed, how it accelerates now more than ever. It's a portrait of a universe in motion, painted with light that left its source long before Earth even existed. There's a quiet poetry in the way we study this. Every telescope, every instrument, is a small mirror turned toward the infinite. We build them with metal and glass, but what they really measure is patience, the willingness to wait for light that began its journey when the first galaxies were young. Each photon that falls onto a detector carries a story billions of years old, and from those stories, we reconstruct the shape of the cosmos, the invisible dance between gravity and dark energy that continues even now. When astronomers speak of the parameter W, they are simply trying to measure how strong that invisible push is, how much pressure the vacuum of space exerts compared to its energy. If that ratio is exactly -1, dark energy behaves like Einstein's constant. If it's slightly different, it might change over time. But these are just numbers wrapped around mystery. Behind them lies something beyond our senses, the quiet persistence of expansion, the slow, steady increase of distance that defines reality itself. With each new generation of telescopes, we refine our understanding a little more. We learn how the universe has grown, how light has aged, how matter has thinned. But the deeper we look, the more it feels like we're staring into our own reflection. The universe expands, and so does our curiosity. The farther galaxies drift away, the more determined we become to follow their light. It's a pursuit that mirrors the nature of dark energy itself, endless, gentle, and unstoppable. And perhaps that's the most human thing about this entire endeavour. We are creatures of gravity, bound to one small planet, yet we reach across billions of light years to measure the expansion of space. We do it not because we expect to find an answer carved in stone, but because asking the question connects us to the vastness. We are the universe trying to understand its own breadth. So when you hear of scientists measuring dark energy, imagine not equations and machines, but people standing under the night sky, tracing invisible patterns with their minds. Imagine them turning mirrors toward the stars, listening for the faintest change in light, the quiet whisper of acceleration. Every map they make is really a portrait of wonder, of a species looking into the dark and deciding to keep looking, even when the darkness itself is the thing they seek. Each new survey, each new image, brings us closer to something profound. Not just the knowledge of how the universe moves, but the awareness that we too are moving with it. Every expansion, every drift, every fading galaxy is part of a grand pattern still unfolding, and every map we draw of the invisible brings us closer to seeing not only the universe's story, but our place within it. Time. 1.5. When scientists speak of dark energy, they often sound like poets describing silence, trying to give shape to something that cannot be seen or touched. To approach that mystery, they turn their gaze not only outward, to the distant galaxies, but inward to the quiet structure of the vacuum itself. What they find there is equally strange. Even nothingness refuses to be empty. The closer we look, the more alive it becomes. The idea that the vacuum is not truly empty might sound impossible, yet it is one of the best tested concepts in modern physics. Even in the absence of matter, the laws of quantum mechanics say that fields, the invisible fabrics underlying all particles, can never be perfectly still. They are restless. They tremble with tiny fluctuations, creating and destroying pairs of virtual particles faster than any clock can measure. These ghostly events happen everywhere, all the time, in every cubic centimetre of space. They flicker into being, then disappear almost instantly, leaving behind the faintest trace of energy, the same kind of energy that could be responsible for the accelerating universe. One of the most elegant demonstrations of this hidden activity comes from an experiment called the Casimir effect. It sounds simple. Take two perfectly smooth metal plates and place them just a few billionths of a meter apart inside an absolute vacuum. Nothing is between them. No air, no particles, nothing at all. And yet, the plates move. They are gently pushed together by a mysterious pressure. The reason lies in the quantum fields that fill the vacuum. Between the plates, only certain vibrations can exist. Shorter waves don't fit in the narrow gap. Outside the plates, all possible vibrations are allowed. The imbalance creates a tiny force, as if the plates are being squeezed by the weight of the vacuum itself. The Casimir effect is incredibly small, weaker than the pull of gravity between two grains of dust, but it's real. It proves that the vacuum is not nothing. It has structure. It has energy. It whispers. And though this energy is faint on the human scale, the universe contains unimaginable volumes of space. When you multiply that whisper by the infinite, it becomes a roar. That roar could be what drives the galaxies apart, the quiet force that fills every corner of the cosmos. But here is where the puzzle deepens. When physicists calculate how much energy these quantum fluctuations should add up to, they get a number that is absurdly, impossibly large. The predicted vacuum energy, based on quantum theory, is roughly 1 followed by 120 zeros, times stronger than what we actually observe. If that were true, the universe would have blown itself apart moments after it began. And yet, here we are, galaxies, stars, people, all existing in a universe that expands gently, not violently. Something cancels out almost all of that energy, leaving only a delicate residue that shapes the cosmos. It's one of the greatest unsolved mysteries in science, a mismatch so extreme that it has been called the worst theoretical prediction in the history of physics. Why is the vacuum's energy so small yet not zero? Some physicists think there may be a hidden symmetry in nature that balances positive and negative energies, nearly cancelling them out. Others suspect that our universe is only one bubble in a vast cosmic foam, each bubble with its own laws of physics and its own vacuum energy. We just happen to live in a bubble where the value of that energy allows stars, planets, and life to exist. In another universe, the vacuum energy might be higher or lower, creating a cosmos that expands too fast for matter to form, or collapses too quickly to survive. In that sense, we might be living in a rare equilibrium, the one version of reality where the forces of creation and destruction hold each other in perfect balance. This idea, that the vacuum energy might vary from one universe to another, has led some thinkers to the concept of the multiverse, a sea of universes bubbling up endlessly, each born from quantum fluctuations of nothingness. If that is true, then our universe is not the only one, but simply one breath among countless others in an infinite expanse of creation. Dark energy in this picture becomes not just a cosmic mystery, but a reminder of how delicately tuned existence really is. Out of all possible realities, ours is one where expansion happens neither too quickly nor too slowly, just fast enough to make stars, to make galaxies, to make us. To explore these ideas, scientists build experiments as precise as art. Some use particle accelerators, smashing protons together at near-light speed, searching for signs of new fields that might interact with dark energy. Others study the cosmic microwave background, the faint afterglow of the Big Bang, for tiny patterns that could reveal how the early universe balanced its energies. Even laboratory physicists, in quiet rooms filled with lasers and polished mirrors, measure how light behaves in near-perfect vacuums, searching for whispers of unseen forces. Every result, every measurement is a clue in this detective story written in equations and photons, and still, the vacuum keeps its secret. The more accurately we measure, the quieter the mystery becomes, as if the universe itself were reluctant to reveal the source of its calm. It's humbling to realise that after centuries of progress, after relativity, quantum theory, and the discovery of the expanding cosmos, we still don't know why the universe exists in this fragile balance. It's as though nature tuned the strings of reality just right, so that creation could play its song for a while before fading into silence. Perhaps that's the lesson hidden in the vacuum's whisper, that perfection is not found in extremes, but in balance. If the vacuum energy were any stronger, galaxies could never have formed. If it were weaker, the universe might have collapsed before stars could shine. The difference between existence and nothingness is a matter of exquisite precision, a tuning so exact that it defies imagination. Out of that balance came everything: atoms, light, and life. It's easy to think of science as the opposite of wonder, but the truth is the opposite. The deeper we explore, the more the universe reminds us how astonishing it is to be here at all. Every experiment that probes the vacuum is also a reflection on our own presence within it. The same quantum fluctuations that ripple through empty space ripple through you. The energy that fills the cosmos also hums quietly in the atoms of your body. You're made of starlight and emptiness, held together by the same laws that shape galaxies and guide time. So the next time you hear the word nothing, remember that it isn't empty. It's a sea of possibility, a canvas of invisible motion that gives rise to everything. The plates in the Casimir experiment, the glow of distant galaxies, even the expansion of the universe. All are ripples on the same quiet ocean. And somewhere in that vast stillness, the universe holds its balance, between being and not being, between silence and song. That balance might be the only reason we exist, and the only reason we can look into the dark and call it beautiful. There comes a point in every story of science where numbers begin to fall silent. The equations may describe the expansion of the universe perfectly. They can tell us how fast galaxies drift apart, how light stretches, how energy curves space. But they cannot tell us why it feels so mysterious, so hauntingly human, to live inside an expanding universe. After all, we are not outside observers. We are inside the very thing that grows. Every second of our lives, every thought, every heartbeat, unfolds within the same expansion that carries galaxies away from each other. When space itself grows, so does the stage on which time and memory play their parts. What does it mean for space to expand? It's tempting to picture galaxies racing outward into some greater void, as though the universe were swelling into an infinite black background. But there is no outside. Space doesn't expand into anything. It expands within itself. The distances between things grow because the fabric of reality is stretching everywhere, in every direction. You're not moving away from the stars. The space between you and them is growing. It's an idea that bends the mind because it bends our intuition of movement. We are so used to motion being relative, one thing moving against another, that we forget it can also be absolute. The space between them changing, even if both stay still. If the universe expands, then time too must stretch along with it. Space and time are two threads of one fabric, intertwined so completely that you cannot pull on one without tugging the other. When we speak of cosmic expansion, we're not only describing distances growing, We're describing time itself being rewoven. Every moment is a little longer than the one before, every beat of cosmic history slightly more spacious. In a universe ruled by dark energy, even time itself is part of the expansion. And what about us, the tiny witnesses? If the distances between galaxies are stretching, then so in principle is the space inside us, between atoms, between electrons and nuclei. Yet the forces that bind matter together are so much stronger than cosmic expansion that we don't feel it. The electromagnetic pull within atoms is billions upon billions of times more powerful than the outward pressure of dark energy. You could wait for 1 trillion years and your atoms would still hold together. On our scale, expansion is invisible. But that doesn't mean we are separate from it. We are woven into the same cosmic fabric, folded into the same breath that stretches galaxies apart. The quiet expansion of the universe happens within us, as much as around us. There's a quiet poetry to that thought. We often imagine ourselves as small compared to the cosmos, but perhaps we are not small. Perhaps we are reflections of it. The same principles that shape galaxies also shape our perception of time, our sense of change, our longing for permanence in a world that never stops moving. The expanding universe is not just a physical process. It's a metaphor written in starlight. Everything drifts apart, yes, but that drift makes room for creation, for new stars, for new worlds, for new ideas. Even in its vast indifference, the universe is generous. Sometimes people ask, if everything's expanding, how can we tell? Shouldn't our measuring tools expand too? It's a fair question, and it touches the edge of philosophy. The answer is that expansion acts on the fabric of space itself, not on the bonds within matter. Our rulers, our atoms, our bodies remain bound by forces that are far stronger than dark energy's pull. The universe expands only where those bonds are weak, in the emptiness between galaxies. On smaller scales, gravity and electromagnetism hold space still. That's why we can look up and see the universe expanding without feeling it. It's as though we live inside bubbles of stability, floating in an ocean that grows between them. And maybe that's a lesson in perspective. On cosmic scales, everything drifts apart. On human scales, we hold fast to one another, to memory, to meaning. We build constellations not in the sky, but in our hearts, shapes of connection drawn across the dark. The expansion of the universe doesn't erase those connections, it makes them precious. The greater the distance between stars, the more beautiful it is that we can still see their light. Science can describe the universe's growth in precise terms, a ratio between its energy and its pressure, an acceleration measured in kilometers per second per megaparsec. But those numbers are only a language for something deeper, the universe's own instinct to move, to breathe, to become. The equations show us how it happens, but not why. They can tell us that space expands exponentially under the influence of dark energy, meaning it grows faster the more it grows, but they cannot tell us what it feels like to be part of that infinite exhalation. That, perhaps, is where science meets wonder. It's easy to mistake expansion for emptiness, but maybe it's the opposite. Expansion creates room for stars to form, for planets to orbit, for life to exist. If the universe had stopped growing long ago, everything would have collapsed under its own weight. The cosmos would be dense and dark without structure or breath. Expansion is the universe's way of keeping itself alive, of maintaining space for possibility. The distances we see, the loneliness of the night sky, are not signs of absence. They are the price of freedom. There's a quiet parallel between cosmic expansion and human experience. We spend our lives expanding, our bodies in childhood, our minds in curiosity, our memories across the years. And like the universe, we slow at times, accelerate at others, driven by invisible forces we don't always understand. We hold on to what gravity we can, family, love, meaning, but still life stretches us. The spaces between our past and our future grow, and we learn to fill them with stories. Perhaps dark energy, in its strange way, is the universe's version of hope, the refusal to stop growing, even in silence. Some physicists have suggested that as the expansion continues, the universe will approach something close to a steady state, an eternal flow of creation at the edges, even as old stars fade away. That may not be literal, but it's a comforting image. The cosmos renewing itself, never collapsing, never entirely at rest. Perhaps that's what dark energy ensures, not a tragic ending, but an ongoing motion, a continuation of being. As you think about this, imagine the universe not as something distant or cold, but as something that breathes with you. The same energy that drives its expansion flows through every atom of your body. When you breathe in, you take part in that rhythm, contraction and release, gravity and expansion. You're not outside the story, you're a line written within it. Every thought you have, every heartbeat, every moment of wonder is a local echo of that grand cosmic pulse. And so, when we speak of the expansion of the universe, we're not just describing physics, we're describing ourselves, our tendency to seek, to grow, to stretch beyond what we know. The galaxies drift apart, but in doing so, they create space for light to travel, for worlds to form, for eyes to open and see. The expansion of the universe is not emptiness expanding into nothing. It is potential unfolding into being. It is the quiet, unstoppable act of becoming. One day, long after our brief time here is over, the galaxies we see will fade beyond sight, but the space that carried them will still expand, and the rhythm of that motion will go on. The universe will continue to breathe, softly and eternally, and somewhere within that breath will linger the memory of those who once looked up and tried to understand it. If you close your eyes and imagine the universe not as a collection of stars or galaxies, but as one vast living thing, you might sense its rhythm. It isn't the quick pulse of a heartbeat or the steady ticking of a clock, but something deeper and slower, a cosmic breath, so vast that it takes billions of years to complete a single inhalation. Gravity is the inhale, drawing everything together. Dust into stars, stars into galaxies, galaxies into clusters. Dark energy is the exhale, gently pushing everything apart, giving space its quiet expansion. Between the two lies balance, the eternal rhythm of creation and release. The idea that the universe breathes is not just a metaphor. In a sense, the cosmos really does alternate between gathering and dispersing. Every star that burns is born from collapse. Every cloud of gas that forms a new world must first fall inward before it can expand again. Even the cycle of birth and death among stars mirrors this pattern. Gravity brings matter together. Nuclear fire pushes it outward. In that interplay, stars live, shine, and die. The universe's expansion is simply that same pattern, scaled up to infinity, the slow inhale of gravity, followed by the long, patient exhale of dark energy. It's easy to think of the expansion as something cold, mechanical, or mathematical. The numbers describe it. The speed of galaxies drifting apart, the ratio between energy and pressure in the vacuum. But the feeling of it is something else entirely. It's the sensation of stillness that hides motion, of silence that hides music. Every moment, space itself grows. It doesn't make a sound, yet it's everywhere, connecting every atom, every beam of light. The fabric of reality stretches not with violence, but with calm, like a sigh too vast for ears to hear. When you breathe in, your body expands slightly. You make space for air to enter. The universe is doing the same thing, but on a scale so large that even light struggles to keep up. Every second, more space appears, between galaxies, between clusters, between everything. The expansion doesn't tear the cosmos apart, it carries it. It is the movement that allows the stars to have room to shine, the galaxies to spin freely, and time itself to flow forward. Dark energy is not destruction, it is motion, the continuation of existence, and yet we often call it dark, as if it were a shadow. But darkness here doesn't mean evil or absence, it means mystery. It's simply what we cannot yet see. The ancient astronomers once thought the heavens were unchanging, eternal. Then we discovered the expansion, the cosmic background glow, the galaxies rushing away. Now we know the universe is alive with motion, shaped by an invisible force that gives it breath. Perhaps, one day, what we call dark energy will seem as ordinary as the light of the sun. Once a mystery, now a fact of being. Some scientists imagine that the universe might one day stop expanding and begin to contract, pulled back by gravity into a final fiery collapse, the Big Crunch. Others believe the expansion will continue forever, ending in the cold quiet of the Big Freeze. But there are also ideas, whispered at the edges of theory, that the universe could oscillate, an infinite series of breaths, each cycle of expansion followed by contraction, like the rise and fall of cosmic lungs. No one knows which version will come true. Perhaps dark energy is constant, ensuring endless expansion. Perhaps it will fade or change. What's certain is that the universe, in all its immensity, will continue to evolve in ways that defy simple endings. When we think of the cosmos this way, it changes how we think about ourselves. We often imagine that we stand apart from it, that we're small observers, staring up from the edge of a tiny world. But we're not outside the universe, we are made of it. The atoms in your body were born in stars, and those stars were born in galaxies woven into the same expanding fabric that carries everything else. The same laws that drive the galaxies apart guide the beating of your heart, the motion of your breath. You're a fragment of the universe, aware of itself, whispering its story back into the night. Even the act of wondering, of asking what dark energy is, or where the universe will go, is part of that same process of expansion. Curiosity itself is a kind of cosmic motion, the mind stretching to fill the space of what it does not yet understand. Every time we look farther, build better telescopes, or imagine new theories, we're participating in the universe's unfolding. We are part of its consciousness, fleeting but real, the universe learning for a brief moment how to see itself. There's a moment, late at night, when the world grows quiet, when the hum of traffic fades, the air stills, and you can almost hear the soft thrum of your own pulse. If you listen carefully in that silence, perhaps you can sense the echo of the larger rhythm, the slow expansion of the cosmos carrying everything outward, galaxies and thoughts alike. We live inside that stillness, inside that gentle movement. Every breath we take is synchronized with it, though we rarely notice. Even as everything drifts apart, it does so together. The galaxies moving away from each other are still part of one universe. The stars that fade are still part of the same continuum of energy. When we feel alone beneath the night sky, it's easy to forget that separation and unity are the same thing. The expansion doesn't divide, it connects through motion. Distance is not absence, it's relationship made larger. The farther the galaxies drift, the more we realise they were once one, and that memory of togetherness still lingers in the glow of the cosmic background radiation, the afterimage of the universe's first breath. So when you look up at the stars, you're not looking out into something foreign. You're looking into yourself, stretched across billions of light years. The atoms in your eyes are made from ancient stars that once collapsed under gravity and exploded, scattering the ingredients of life. You're a product of the inhale, carried forward by the exhale. The same expansion that propels galaxies through space is also the reason your world exists at all. Without it, there would be no distance for light to travel, no time for stars to form, no place for consciousness to emerge and ask, why? Perhaps that is the final lesson of dark energy, that creation never really stops. The universe is not a single event that happened long ago. It is happening still, everywhere, quietly, continuously. Space grows, time flows, stars are born, and so are ideas. In every widening moment there is room for something new, and so, if you find yourself awake one night, listening to the silence, remember that you are hearing more than stillness. You're hearing the soft exhalation of the universe, the steady expansion that has been unfolding since the dawn of time. You are part of that breath. Every heartbeat, every thought, every gentle rise and fall of your chest is a reflection of it. The universe breathes, and so do you. And though everything drifts apart, it does so together, in rhythm, gravity pulling in, dark energy pushing out, existence suspended between the two. Perhaps that is what eternity really means. Not endless time, but endless motion. The infinite inhale and exhale of reality itself. So let it all expand. Let the galaxies drift. Let light travel farther than you can imagine. Somewhere in that quiet, in the space between stars and silence, the universe continues its breath, calm, endless, and alive. And for this brief shining moment, you are part of it,